and this is the average, the 1/4, because there are 4 independent examples here. And then we have the 4 examples and their mean squared error, the squared error, and then this makes it the mean squared error. So therefore, we calculate the squared error, and then we normalize it to make it the mean over the examples. And there's 4 examples here. So now when we come to the gradient accumulation version of it, this here is the gradient accumulation version of it, where we have grad accum steps of 4, and I reset the gradient. With grad accum steps of 4, and now I'm evaluating all the examples individually instead and calling loss.backward on them many times. And then we're looking at the gradient that we achieve from that. So basically now we forward our function, calculate the exact same loss, do it backward, and we do that 4 times. And when we look at the gradient, you'll notice that the gradients don't match. So here we did a single batch of 4, and here we did 4 gradient accumulation steps of batch size 1. And the gradients are not the same. And basically the reason that they're not the same is exactly because this mean squared error gets lost. This 1/4 in this loss gets lost, because what happens here is the loss objective for every one of the loops is just the mean squared error, which in this case, because there's only a single example, is just this term here. So that was the loss in the 0th iteration, same in the 1st, 3rd, and so on. And then when you do the loss.backward, we're accumulating gradients. And what happens is that accumulation in the gradient is basically equivalent to doing a sum in the loss. So our loss actually here is this, without the factor of 1/4 outside of it. So we're missing the normalizer, and therefore our gradients are off. And so the way to fix this, or one of them, is basically we can actually come here and we can say loss equals loss divide 4. And what happens now is that we're scaling our loss. We're introducing a 1/4 in front of all of these places. So all the individual losses are now scaled by 1/4. And then when we backward, all of these accumulate with a sum, but now there's a 1/4 inside every one of these components. And now our losses will be equivalent. So when I run this, you see that the gradients are now identical. So long story short, with this simple example, when you step through it, you can see that basically the reason that this is not correct is because in the same way as here in the MSE loss, the loss that we're calculating here in the model is using a reduction of mean as well. So where's the loss? F dot cross entropy. And by default, the reduction here in cross entropy is also, I don't know why they don't show it, but it's the mean loss at all the b by t elements, right? So there's a reduction by mean in there, and if we're just doing this gradient accumulation here, we're missing that. And so the way to fix this is to simply compensate for the number of gradient accumulation steps, and we can in the same way divide this loss. So in particular here, the number of steps that we're doing is loss equals loss divided gradient accumulation steps. So even sort of gets the modification. But in the same way exactly, we are scaling down the loss so that when we do loss step backward, which basically corresponds to a sum in the objective, we are summing up the already normalized loss. And therefore, when we sum up the losses divided by grad outcome steps, we are recovering the additional normalizer. And so now these two will be, now this will be equivalent to the original sort of optimization because the gradient will come out the same. Okay, so I had to do a few more touch-ups and I launched the optimization here. So in particular, one thing we want to do, because we want to print things nicely, is, well, first of all, we need to create like an accumulator over the loss. We can't just print the loss because we'd be printing only the final loss at the final microstep. So instead we have a loss accum, which I initialize at 0, and then I accumulate the loss into it. And I'm using detach so that I'm detaching the tensor from the graph, and I'm just trying to keep track of the values.